Hello all. Now we will see the topic that is the transmission lines. In the transmission line, the line parameters are resistance, which is denoted by R, capacitance denoted by C, inductance denoted by L, and conductance denoted by G. This is the line of cascaded T section. You can observe here these four parameters are mentioned in this circuit diagram, that is the L, R, C and G. This line represented in terms of cascaded connection of equivalent T section, and what is the uniform transmission line? That is the parameters are uniformly distribution along the entire length of transmission line, so it is called as a uniform transmission line. Next one, that is the RF equivalent circuit. In RF equivalent circuit, frequency is the radio frequency. The inductive reactance is much larger than the resistance for the radio frequency, and the capacitive susceptance is much larger than the shunt resistance. Here, the RF equivalent circuit is shown, that is the L and C. Here, the reflection spot question is that what are the primary constants of transmission lines? You just pause the video and write the answers in your journal. The primary constants of transmission lines are R, L, G and C. So we will see these constants in detail. So first one, resistance, loop reactance per unit length of line, and its value is depend on the cross-sectional area of conductors. So the sum of resistance of both the wires for unit line length. Second one, that is the inductance. This is the loop inductance per unit length of line, and sum of inductance of both the wires for unit line length. Third constant is conductance. It is a shunt conductance between two conductors. The dielectric medium between two conductors is not perfect. So, the some leakage current passes through it, and it produces the leakage conductance which is distributed all along the line. And the last constant is capacitance. It is the shunt one, that is the present in between two lines, and the dielectric medium between two conductors is perfect. It produces the effect of capacitance which is distributed all along the line. Here, for the transmission line we have seen the primary constants. Now we will go through these secondary constants. First one is characteristics impedance, second propagation constant, third attenuation constant, and fourth one is a phase constant. So, characteristics impedance consists of series and shunt impedances and must have an input impedance. For the transmission line, this input impedance will depend on the type of line, its length and transmission at the far end. So, the definition of characteristic impedance of the transmission line is the impedance measured at the input of this line when its length is infinite. How to calculate this characteristics impedance? The formula is Z0, that is the characteristics impedance, is equal to under root of Z by Y. Here Z is the series impedance per unit length, that is equal to R plus J omega L, and Y is equal to G plus J omega C. So Z0 is equal to under root of Z divided by Y. Next one is propagation constant. It is also called as propagation coefficient. It shows the nature in which the waves are propagated along the line, and it also gives the information about the variation of voltage and current. So the definition is the natural logarithm of vector ratio of steady state voltages and the current entering and leaving the structure. So you can calculate your propagation constant, that is log of the base E Is divided by IR in the complex term and varies with frequency. Next one, attenuation constant. Attenuation constant, that is, we know that propagation constant is gamma is equal to alpha plus j beta. From this gamma, that is the alpha is attenuation constant. This is the real part and it determines the reduction and attenuation in voltage or current along the line. So the unit for this attenuation constant is Nepper per kilometer and the phase constant. In this, beta is phase constant and it is the imaginary part. It determines the variation in the phase position of voltage and current along the line and the unit is radians per kilometer. Wavelength. We can observe this waveform. So, the distance in which the wave traveling along the line causes a phase shift of radians. So, the distance between two successive positive or negative peaks is called as a wavelength. So, you can observe this diagram and you can find out the wavelength using or by considering the positive or the negative peaks. So, we can say that lambda is equal to 2 pi upon beta. Phase velocity or velocity of propagation. The signal of a single frequency which is propagating along the line at a particular frequency. So, suppose the wave travels a distance lambda in time period t. So, we can say that t is equal to 1 by f, that is the frequency, and Vp, that is velocity of propagation, is equal to distance upon time is equal to lambda by t is equal to lambda f. What is the lambda? Lambda is the 2 pi upon beta. So, if you simplify your velocity of propagation formula, then you will get Vp is equal to 2 pi f divided by beta or omega divided by beta. Group velocity. So, in the transmission line, different frequencies travel with the different velocities. So, the velocities are produced by group of frequencies. So, in group velocity which is less than your phase velocity. So, it is denoted by Vg, which is equal to d omega divided by d beta. Then skin effect. Skin effect is very important in transmission. So, the phenomena arising due to unequal distribution of current over the entire cross section of the conductor being used for long distance power transmission is referred to as the skin effect in transmission line. It does not have much role to play in case of a very short length, but with increasing the effective length of the conductor, skin effect increases considerably. So, thank you.